Hello everyone, I'm Emad Hashemi and I'm with you an advanced data visualization in Python course. Due to the importance of data visualization, there are many pieces of training on this subject that teach basic and preliminary data visualization. But in this course, we will teach you how to visualize your data in an advanced way in Python. In this course, we even teach 3D visualization so you can specifically visualize your data and draw graphs using Python codes. You can use this course to visualize your data from managers, scientific papers, work projects, university classes, personal websites, and even advertisements. In the following, we will see some of the diagrams that you will learn in this course. Visualization in 3D is sometimes effective and sometimes inevitable. Here we present some examples that will satisfy the most frequent requirements. However, Matplotlib is mainly focused on plotting and mainly in 2 dimensions. There are different extensions that enable us to plot over geographical maps to integrate more with Excel and plot in 3D. These extensions are called toolkits in a Matplotlib world. Toolkit is a collection of specific functions that focuses on one topic, such as plotting in 3D. Popular toolkits are Basemap, GTK tools, Excel tools, NatGrid, Access Grid, and Mplot3D. We will explore more of Mplot3D in this recipe. The toolkit mpl_toolkits.mplot3d provides some basic 3D plotting. Plots supported are scatter, surf, line, and mesh. However, this is not the best 3D plotting library. It comes with Matplotlib and we are already familiar with the interface. Basically, we still need to create a figure and add desired axes to it. The difference is that we specify 3D projection for the figure and the axes we add are axes 3D. Now we can use almost the same functions for plotting. Of course, what are different are the arguments, for we now have 3 axes that we need to provide data for. For example, the function mpl_toolkits.matplot3d.axes3d.plot specifies xs, ys, zs, and zdir arguments. All others are transformed directly to matplotlib.axes.axes.plot. We will explain these specific arguments. Xs and ys, there are coordinates for x and y axes. Zs, this is the value or values for z axis. It can be 1 for all points or 1 for each point. Zdir, this will choose what will be the z-axis dimension. Usually this is zs, but can be xs or ys. There is a method rotate_axes in a module mpl_toolkits. Matplotlib.art3d that contains 3D artists code and functions to convert 2D artists into 3D versions, which can be added to Access 3D to reorder coordinates so that the axes are rotated along with Z dire. The default value is Z. This is the code to demonstrate the concept explained. The preceding code produces the following diagram. We had to do the same preparation work as in the 2D world. The difference here is that we needed to specify the kind of backend. Then we generate some random data, for example, 4 years of sale from 2011 till 2014. We needed to specify the Z values to be the same for the 3D axis. We pick the color randomly from the color map set, and then we associated each Z order collection of XS, YS pairs. We would render the bar series. Other plotting from 2D Matplotlib is available here. For example, a scatter with a similar interface to plot, but with added size of the point maker. We are also familiar with contour, contour F, and bar. The new types that are available just in 3D are wireframe, surface, and tree surface plots. The following code example plots tree surface plot of popular triangle functions, or more mathematically a hyperbolic paraboloid. Similar to 3D bars, we might want to create 3D histograms. They are used to easily spot correlation between three independent variables. They can be used to extract information from images where the third dimension could be the intensity of a channel in X and Y space of the image under analysis. In this recipe, we will learn how to create 3D histograms. To recall, a histogram represents a number of occurrences of some value in a particular column, usually called bin. The three-dimensional histogram then represents a number of occurrences in a grid. This grid is rectangular over two variables that are data in the two columns. For this computation, we will 1. Use NumPy because it has the function to compute a histogram of two variables. 2. Generate X and Y from normal distributions but with different parameters to be able to distinguish the correlation in the resulting histogram. 3. Plot the scatter plot of the same dataset to demonstrate how different is the display of a scatter plot to 3D histogram. Following is the code sample to implement the described steps. the preceding code will give the following output. We prepare a computer histogram using np.histogram2d that returns our histogram or hist and x and y being x. Because for the bar d3d function we need coordinates in x and y space, so we need to compute the common matrix coordinates, and for that we use np.meshGrid that combines the x and y positional vectors into the 2D space grid or matrix. We can use this to plot bars in the xy plane locations. The variables dx and dy represent width of the base of each bar, and we want to make this constant. Hence, we give it a 0.1 point value for every position in the xy plane. The value in the x-axis, or dz, is actually our computer histogram in variable hist that represents the count of common x and y samples at a particular bin. A scatter plot in preceding plots displays the 2D axis that also visualize correlation between two similar distributions, but with a different set of starting parameters. Sometimes 3D is what gives us more information and resonates what the data is containing in a better way. As more often 3D visualization are more confusing than 2D, it is advised to think twice before we choose them over 3D. Analogous to the contour plots we explored in density and contour plots, Matplotlib contains tools to create three-dimensional relief plots using the same inputs. Like two-dimensional x.contour plots, x.contour3D requires all the input data to be in the form of two-dimensional regular grids with the z data evaluated at each point. Here we'll show a three-dimensional contour diagram of a three-dimensional sinusoidal function. Sometimes the default viewing angle is not optimal, in which case we can use the viewInit method to set the elevation and azimuthal angles. In the following example, we'll use an elevation of 60 degrees, that is 60 degrees above the XY plane, and an azimuth of 35 degrees, that is rotated 35 degrees contour clockwise about the z-axis. Again, note that this type of rotation can be accomplished interactively by clicking and dragging when using one of Matplotlib's interactive backends. Two other types of three-dimensional plots that work on gridded data are wireframes and surface plots. These take a grid of values and project in onto the specific three-dimensional surface and can make the resulting three-dimensional forms quite easy to visualize. Here's an example of using a wireframe. A surface plot is like a wireframe plot, but each face of the wireframe is a filled polygon. Adding a color map to the filled polygons can aid perception of the topology of the surface being visualized. Note that through the grid of values for a surface plot needs to be two-dimensional, it need not be rectilinear. Here is an example of creating a partial polar grid, which when used with the surface plot can give us a slice into the function we are visualizing. Matplotlib was initially designed with only two-dimensional plotting in mind. Around the time of the one release, some three-dimensional plotting utilities were built on top of Matplotlib's two-dimensional display, and the result is a convenient set of tools for three-dimensional data visualization. Three-dimensional plots are enabled by importing the Mplot3D toolkit included with the main Matplotlib installation. Once the submodule is imported, a three-dimensional axis can be created by passing the keyword projection equal 3D to any of the normal axis creation routines. With this three-dimensional axis enabled, we can now plot a variety of three-dimensional plot types. Three-dimensional plotting is one of the functionalities that benefits immensely from viewing figures interactively rather than statically in a notebook. Recall that to use interactive figures, you can use Matplotlib Notebook rather than Matplotlib Inline when running this code. The most basic three-dimensional plot is a line or collection of scatter plot created from set of x, y, z triples. In analogy with the more common two-dimensional plots discussed earlier, this can be created using the x.plot3d and x.scatter3d functions. The code signature for this is nearly identical to that of their two-dimensional counterparts. Here, we'll plot a trigonometric spiral along with some points drawn randomly near the line. Notice that by default, the scatter points have their transparency adjusted to give a sense of depth on the page. While the three-dimensional effect is sometimes difficult to see within a static image, an interactive view can lead to some nice intuition about the layout of the points. For some applications, the evenly sampled grid required by the above routines is overly restrictive and inconvenient. In these situations, the triangulation-based plots can be very useful. What if rather than an even draw from a Cartesian or a polar grid, we instead have a set of random draws? We could create a scatter plot of the points to get an idea of the surface we are sampling from. This leaves a lot to be desired. The function that will help us in this case is x.plot_trisurf, which creates a surface by first finding a set of triangles formed between adjacent points. Remember that x, y, and z here are one-dimensional arrays. The result is certainly not as clean as when it is plotting with a grid, but the flexibility of such a triangulation allows for some really interesting three-dimensional plots. For example, it is actually possible to plot a three-dimensional Mobius strip using this, as we'll see next. A Mobius strip is similar to a strip of paper glotted into a loop with a half twist. Topologically, it's quite interesting because despite appearances, it has only a single side. Here we will visualize such an object using Matplotlib's three-dimensional tools. The key to creating the Mobius strip is to think about its parameterization. It's a two-dimensional strip, so we need two intrinsic dimensions. Let's call them theta, which ranges from 0 to 2p around the loop, and w, which ranges from -1 to 1 across the width of the strip. Now from this parameterization, we must determine the x, y, and z positions of the embedded strip. Thinking about it, we might realize that there are two rotations happening. One is the position of the loop about its center, what we've called theta, while the other is the twisting of the strip about its axis. We'll call this phi. Now we use our recollection of trigonometry to derive the three-dimensional embedding. We'll define R, the distance of each point from the center, and use this to find the embedded x, y, and z coordinates. Finally, to plot the object, we must make sure the triangulation is correct. The best way to do this is to define the triangulation within the underlying parameterization, and then let Matplotlib project this triangulation into the three-dimensional space of the Mobius strip. This can be accomplished as follows. Combining all of these techniques, it is possible to create and display a wide variety of three-dimensional objects and patterns in Matplotlib. We can use the NumPy array to create the data points and Matplotlib to plot the data points in the plot. We need discrete data points to plot the scatter plots, which can be achieved by arrange function, linear space function, etc. First, as customary, we imported all the necessary libraries and packages in our code. Imported NumPy and Matplotlib library using the import statement of Python. Next, we created a user-defined function, a three-dimensional scatter. This function takes 6 parameters, namely x1, y1, z1, x2, y2, and z2. Under this function, we created if figure objects and specified the size of the figure. Next, we created an axis object using the plot.axis function. We have passed the argument projection equal 3D to create a three-dimensional workspace. Next, we plotted the graphs using x.scatter3D function. We passed the necessary parameters to the function. We also used another optional parameter, namely color. We used similar codes for plotting the second plot too. We also set the title to the plot using the plt.title function. We set legends to the plot using the plt.legend function. We then displayed the graph using the plt.show function. Next, we created the main function. Under this function, we created data points for both plots. We used both arrange function and random functions of the NumPy library for creating those data points. we call the three-dimensional scatter function. Finally, we call the main function using the following lines of code. We can use the linspace function of NumPy to create continuous data points. This will be useful in plotting the line graph since the line graph is a continuous graph. First, we imported all the necessary libraries and packages in our code using the import statement. We have imported the libraries using their alias names for convenience in writing our codes further. Next, we created a user-defined function named line_3D, which takes 6 arguments, namely x1, y1, z1, x2, y2, and z2. Under this function, we first created the figure object and specified the size of the figure in our code using the fixed size equal 3D attribute. Next, we plotted the plots using the plot3D functions. We also set the title to the plot and displayed this graph. Next, we created the main function. This is the main driving code of the program. Under this function, we created data points for the axes for both plots. We use the linspace function to generate continuous data points. We also use the power function to plot the polynomial function. We then call the line_3D function. Finally, we declare the main function as the driving code of our program using the following lines of codes. The surface graph is a three-dimensional representation of Python. As the name suggests, it represents a functional relationship between two independent variables, say x and z, and the value of y represents the functional value itself. This plot is very similar to the wireframe plot, except for the fact that unlike the wireframe plot, the points are filled with respective polygon figures. Such plots are extensively used in the field of mathematics and economics, where there is a requirement for plotting functions of more than one variable. This tutorial will explain how to plot the surface graph in 3 dimensions. The surface function can do the surface plot in 3 dimensions in Python Matplotlib. 3 parameters are essential for this function. They are the values of x, y, and z respectively. Other parameters are optional and we are free to choose for them. First, we imported all the necessary libraries and packages in our code using the import statement of Python. We have used the alias names for convenience in our code. Next, we have created a user-defined function named surface, which takes 3 arguments, namely x, y, and z. Under this function, we first created the figure object in which we specified the size of the figure using the fixed size attribute. We have set the dimension of the figure to be 9 and 9. Next, we created the axis object. We have passed the attribute projection equal 3D in this function to specify that we want a three-dimensional space. We plotted the surface graph using the plot_surface function of Python Matplotlib. We have first passed the three parameters x, y, and z, which are essential to plot the surface graph. We also specified the color of the plot as white. Next, we use the title function to provide the title to the graph. Finally, we use the plt.show function to do. Next, we created the main function, which is the main driving code of the program. Under this function, we created the data points for the plot. We use the np.outer, np.linspace, np.ones functions to create data points for the x-axis. We use the np.outer function to create multidimensional arrays. It takes two arguments. First is the number array, which should be one-dimensional. The following argument should be another array which should be one-dimensional in shape. The np.ones function generates a NumPy array with all the present elements to be 1. It takes one argument that specifies the number of elements present in the array. The linspace function is used to generate data points between two numbers with some specified iterations. It takes three arguments, namely start, end, and iteration. The start defines the starting number for the iteration. The end defines the last number up to which the iteration should take place, and the iteration is the iterating step of the iteration. Next, we create data points for the y and z axes. Note that we used a function z and implemented it in our code. Notice that the x and y are independent variables, and z here is the dependent variable on x and y. Hence, it is clear that we are plotting a surface graph. We call the surface function by passing the required arguments x, y, and z. Finally, we call the main function using the following lines of code. Gradient surface plot in 3D. The gradient surface plot combines the three-dimensional surface plot and the contour plot. A contour plot is a graphical method for expressing a three-dimensional surface that involves drawing contours on a two-dimensional format using constant z slice theta. In such a plot, the part of the graph at a higher altitude is given different contrast of color compared to the altitude with lower heights. First, we imported the necessary libraries and packages in our code using the import statement of Python. Next, we created a user-defined function named surface, which takes three arguments x, y, and z. Under this function, we first define the color map object using the get_cmap function. We have passed the parameter blues to this function. Note that this is not the same as the color argument. Look up the Python Matplotlib documentation to know the available values of the attributes of this function. Next, we created the figure object in the code using the plt.figure function and specified the size of the figure using the fixed size attribute. Next, we created the axis object using the plt.axis function, and we specified the attribute projection equal 3D to specify a three-dimensional plot. Next, we plotted the graph using the x.plot_surface function. We first passed the necessary parameters to the code, the values of x, y, and z. We also used another attribute named the CMap and specified the value of color map to this attribute. Next, we set the title to the function using the plt.title function. We use the color bar function to plot the color bar along the surface graph in the plot. We specified other arguments aligned with this function too. For example, the surface_graph is the first argument specifying which plot the color map should be line to. The shrink specifies the size of the color bar in comparison to the height of the surface graph, and finally the aspect specifies the aspect ratio of the color bar. The aspect ratio is defined as the length ratio to the color bar's breadth. Next, we displayed the graph using the plt.show function. Under the surface function, we created the main function, which is the main driving code of the program. Under this function, we first created the data points. We used the NumPy arrays to create data points for the x, y, and z values. We explained this in the previous code. We only changed the function in this example. Next, we call the surface function and pass the required arguments in a function. We finally call the main function using the following lines of code. Next, we created a user-defined function named Wireframe, which takes three arguments x, y, and z. Under this function, we first created the figure object using the figure function of Matplotlib.pyplot. We specified the size of the figure to 9 and 9. Next, we created the axis object using the add_subplot function. Alternatively, we can also use the plt.access function to create the access. The only difference is that the access function will create only one access object, whereas the add_subplot function will add multiple subplot access in a figure. Next, we plotted the graph using the plot_wireframe function. Under this function, we first passed all three parameters x, y, and z. They are critical parameters in a function. Otherwise, Python will throw an error in a code. We also passed other arguments in a function like rstride, cstride, and color to the function. Next, we set title to the graph using the plt.set_title function. Now we have displayed the graph using the plt.show function. However, in Jupyter Notebook, this is optional to use. After the wireframe function, we created another function named the main function. This is the driving code of the program. Under this function, we created the data point for the x, y, and z. We used the NumPy array to create those data points in a code. We used np.outer, np.linspace, and np.once function in a code. The np.linspace takes three arguments: start, end, and several elements. The start defines the starting number of the array to be created. The end defines the last number up to which the iteration should occur, and the last number defines the total number of uniformly spaced data points generated in a code. The np.once function generates arrays with 1 as the only element members. This function takes only one argument, which is an integer. This defines the number of elements that should be present in an array. The np.outer function creates array-like objects. It mainly takes two arguments in a code. The first is the one-dimensional array and the second is another one-dimensional array. The result is an array of the same size as the second array. Finally, we call the wireframe function. It is a void function, hence it does not return anything. Next, we call the main function using the following lines of codes. We can create multiple wireframe graphs in exact figure using Python's Matplotlib_wireframe function. We can use all the associated attributes with the function. First, we created all the necessary libraries and packages in the code. We imported Matplotlib.pyplot module and NumPy library using the alias names. Next, we created a user-defined function named the wireframe function. This function takes 4 arguments, x, y, z1, and z2. Under this function, we first create the figure object. We specify the size of the figure using the fixed size attribute. Next, we created a subplot in the code using the add_subplot function. Under this function, we specify the attribute projection equal 3D to specify that we need a three-dimensional plot in a figure. Next, we use the plot_wireframe function to plot the figure. For the first figure, we first pass the x, y, and z1 parameters, and for the second figure, we pass the x, y, and z2 parameters. Note that these parameters are necessary, otherwise Python will throw an error while interpreting the code. We specified separate colors for the figures to distinguish them figures for the one another. Next, we added a title to the graph using the set_title function. We then display the graph using the plt.show function. Now we created the main function, which is the main driving code of the program. We created the data points for the x, y, and z axis for both plots using the NumPy arrays. We call the Wireframe function. Finally, we declare the main function as a driving code using the following lines of codes.